Hi, my name is Manish Gupta, and in this video, I'm going to talk about tree-based methods for extreme classification. So let's start with the major challenges for extreme classification, and then we will see how these tree-based methods can be designed. Okay. So essentially, recall that extreme classification is the task where you have data points and you want to assign a label or a set of labels to the data point given a huge set of labels, right? So extreme classification, extreme here essentially stands for the large label space. And from this label space, you want to basically choose a subset of labels that relate or that are relevant to a data point. Right? So in that sense, it is a multi-label classification problem, and where the label set is very large. Okay. So at train time, you want to learn this function f, which can basically take a data point and map it to a subset of the labels. While at test time, you want to apply the function f on a new data point and essentially predict the right subset of the labels that applies to this new data point. Now, think of sort of applying decision trees for this problem. So, decision trees, remember, are based on this algorithm where you essentially have some labeled training data and you want to sort of create a tree starting from the root node. You have to choose which attribute to split on and then, what order those attributes should be and so on. And remember, there are various criteria like information gain, Gini index, entropy, and so on. So as to decide what is the right attribute to split on. Okay. So if you think from that perspective, there are four challenges when you want to apply decision tree kind of logic to extreme classification problems. First, there are millions of labels, so the scale is a big challenge, right? Lots of labels rather than, you might have studied decision trees from perspective of binary classification problems or multi-class classification problems, but maybe classes up to like 10 or 100. But here we have millions of labels, millions of classes. The second thing is, how do you get good quality annotated training data at that scale, right? So essentially, if there are millions of labels, you should at least have, let's say, a few points per label, few data points per label. Where do you get these kinds of good quality annotated data? How do you train such a high capacity classifier in a reasonable amount of time? So, to be able to train such a classifier, you need to have like lots of parameters and lots of learnable parameters in this classifier so that it can actually give you good results, good accuracy. But at the same time, you have to also ensure that the training should not take too long, right? So that's the third problem. The fourth problem is, how do you make predictions in a few milliseconds? Whenever you want to deploy these kinds of things, latency is a primary concern. And then how do you make predictions in a few milliseconds given such a high capacity classifier, which can give you accurate results over a label set of a few millions? Okay. So here is an example problem. So finding good bid phrases, right? So essentially, given a particular ad, let's say this Geico ad, what you want to do is to come up with some good bid phrases. So phrases that these advertisers could use to put up bids on advertising exchanges, right? So essentially, what has been found is that, primarily to do these kinds of problems, people essentially either manually design these bid phrases or sort of try to figure out good bid phrases using query logs. So you have an ad and you have a query. You can call that as a bid phrase, potential bid phrase. And then what you want to do is to basically learn a classifier so as to establish the relevance between the query and between the ad and the bid phrase. Okay. So KEX is one such system, KEX, right? Which sort of figures out the relevance between an ad and a bid phrase. And then basically whichever bid phrase is most relevant to the ad, those are suggested as relevant bid phrases. Of course, above a certain threshold, you want good quality. So basically relevance above a threshold for a ad and a bid phrase pair, you basically can suggest those as relevant bid phrase for this ad. So if none of them turn out to be above the threshold, you basically say that no predictions have been made, right? So as you see in these cases, this case and this case, no predictions were made because none of them were above the threshold value. So they use a binary logistic regression classifier because you have just two things, an ad and a bid phrase, and essentially you want to predict whether it is 0 or 1. So use a binary logistic regression classifier. You cannot suggest bit phrases. So now to be able to do this in reasonable amount of time at inference time, what you do is to basically take the ad landing page and take all the words and phrases that are mentioned on that ad landing page and consider them as candidates. Now, so therefore, you cannot suggest bit phrases which are not present on the ad or the ad landing page. Okay. And what is observed is that overall KEX leads to low accuracy, mainly because it cannot really suggest new phrases which are not there on that landing page at all. And in general, it basically just is just based on this relevance notion. And in 2013, when this paper was actually published, KEX was not really very. I mean, the relevance matches were not that powerful anyway. Okay. One way to make KEX better is to basically use something called as KSP on top of KEX, which is actually used here in the figure that you see there. So KSP improves on KEX by actually combining many techniques for expanding this candidate set. So expanding a seed set of bit phrases based on how users rewrite queries in a session, co-click and co-bid information. So using co-occurrence information, what KSP tries to do is to expand on a seed set of bit phrases and therefore hopefully gives you better coverage, right? That's that. But as you observe in these various cases, in these 4 different cases, the multi-label random forest method, along with semi-supervised learning, gives way better results compared to KEX and KSP. And that is why our interest will be in knowing what is this multi-label random forest method. Okay. So that's that. Again, these are not deep learning methods. These are like pure. These are old methods. They are pure, pure core machine learning, non-neural network based methods. Okay, but they work well. So if you basically notice, MLRF plus SSL basically gives you way better results compared to KEX plus KEX plus KXP, even when KEX plus KXP can give you some results. Okay. So how do these MLRFs work? So MLRFs are multi-label random forests, as it says. Now, remember in this particular case of the query to add matching, there are the label space is about 10 million queries. Okay. And the great point about MLRFs is that you can actually train this classifier on 90 million training points. So there are 90 million training points approximately. With 10 million labels, right? 10 million labels and 6 million features. So in less than 1 day on a cluster of 1,000 nodes. So and these nodes basically are CPU nodes, remember? So yeah, I mean, today's world is deep learning world. So, but in 2013, nodes would just mean CPU nodes. Okay. So that's that. Now, for each training point, so each training point basically corresponds to an ad. So you have an ad and you want to basically come up with the bit phrases for that ad. So each training point is represented using a TF-IDF vector of size 6 million. Okay. So, and this TF-IDF vector is actually derived from ad landing pages. And the labels, of course, are the queries or the bid phrases which are relevant, and they are basically derived using the query to add click graph. So from the retrospective data, you basically look at past data, and then for different queries, people clicked on some ads. You basically consider them as relevant if they click more frequently. Okay. So what MLRF approach does is to basically take these training points in the training data and essentially train a whole bunch of trees. So as you see there, you train 3 different trees or more trees, and when a new data point comes in, for example, a new ad, and you basically want to, or a new user here, and you want to recommend some items to the user, or there is an ad and you want to recommend bit phrases for that ad. You basically pass the features of the input to each of those trees, and depending on which branch you take, either you take that one or that one or that one, you land up in some leaf. So, and depending on the label distribution in this leaf, you basically give appropriate weights, or you sort of aggregate, and you finally get the weights over different labels, and then you choose the top few labels and return them as the result, return them as the matched label result. Okay. So how do you build these trees? Now you build trees in the feature space like you typically do in decision tree framework, okay? And you build multiple trees, and that is why they're called as random forests, okay? So each, in the previous video, I sort of said that, hey, you would want your label space to be sort of, your set of labels to be split across different branches of the trees, so that finally, when you end up in a leaf, you're left with very few labels. But the way this is achieved is by actually building trees in feature space. So, and this basically still is okay because each region of feature space typically contains only a small number of active labels. So even if you are dividing your feature space or creating your trees such that each node splits, the feature space into parts, actually you're also partitioning your active labels, right? So the way this works is basically by determining the region in which, so at reference time when a new point is going to come, you're basically going to determine the region where the new point lies by traversing the tree. And then you sort of focus a multi-label classifier on only those labels that are active in that region. So imagine like learning a special multi-label classifier for a particular leaf node in a tree. Okay. So each individual child, left child and the right child, has to deal with not only fewer training data points, but also fewer labels. So since there is a lot of correlation between the feature space of the training points and the label space, therefore, when you split on the training point, using the feature space, you actually end up also splitting with respect to labels in that sense. So you keep growing the tree until the number of active labels in each leaf node is logarithmic in the total number of labels, right? So typically when you design decision trees, you of course have pruning and so on, but you can continue to keep growing the tree until each node is homogeneous. Now in this case, nodes don't become homogeneous, but you essentially have a threshold on active labels. So if the number of active labels in any leaf node is less than log of the total number of labels, you sort of stop. Okay. Now, how do you split each node? So, in MLRFs, this particular algorithm, the authors basically propose using the Gini index. So you essentially select the feature and the threshold for that feature based on the Gini index. In some ways, what you want to do is in a greedy way, you want to minimize the Gini index, which is basically which is basically this formula, right? And in this formula, this part is essentially for the left child, the lower part is for the right child. So L stands for left, R stands for right. NL is basically the number of data points in the left node, and R is the number of data points in the right node. So essentially, it's sort of weighted with respect to the data points in the two left and the right child. Okay. K is the total number of labels. K is the total number of labels. So it's similar to the number of classes, or rather, it's exactly the same as the number of classes which exists in typical Gini index computation. And then the computation is a probability of LK, probability of the label being active, probability of the label K equal to 1 in the left part, left child, multiply 1 minus probability of LK equal to 1 in the left child. And then this part is probability of LK equal to 1 on the right child, multiply by 1 minus probability of LK equal to 1 on the right child. So now, how are these probabilities calculated? So let's basically just focus on this particular probability and see how this is calculated. So probability of a label in the left child basically is calculated over all the points that are in the left child. So essentially, if you look at all the all the data points which are in the left child, you can just sum over all those data points. So remember, each data point is associated with several labels. So you compute the probability of the label LK being active given a particular data point, multiply the probability of that data point. Okay. So now we basically further look at how are these two values computed. So if you basically look at this guy now, then you see a particular data point may be related to some different labels. So if you look at overall set of labels, if the data point was associated with 10 labels, you would say that the probability of LK equal to 1 given I is 1 over 10. Right. So that is what is being calculated here. So YIK is basically the actual label, or other, is the label K valid for the data point I or not, right? So YIK is, can take only two values, 0 or 1. So if the label is active, it basically takes a value 1. If it is not, or if it is not relevant or active, basically it takes a value of 0. Okay. Now, probability of I, you would think that, hey, each data point should have the same weight, big deal, right? But, what is interesting to do is to essentially consider the following. So, if a particular data point is associated with more labels, then you would consider its probability higher, right? So in the sense that head labels should sort of contribute more to the probability of I rather than contributing just as much as tail labels. Okay. So that's that. So that's how basically this MLRF or the trees in the MLRF are trained. They're basically trained using the same Gini index. It's just that the way Gini index is defined differs in the extreme classification space. Okay. At prediction time, what happens? At prediction time, a new ad landing page appears, and essentially you look at its features, the 6 million vocabulary based TF-IDF feature vector, right? You basically pass it down the tree to reach a leaf node with a different active label set. So you essentially pass down the tree, you reach a leaf node, and then you basically look at the active label distribution across the leaf nodes from different trees in the entire MLRF, right? And then you basically take care of the most popular labels, and those are the labels that you recommend to the advertiser. Okay. Now, what happens is that there are missing labels and incorrect labels in the data set, in any training data set, right? So training data sets are never obviously clean. So essentially, if you look at any data set, you would have missing labels, especially when you have a very large label space. So tail labels are several times missing, right? Sometimes there are incorrect labels also. So for example, for a particular ad, let's say for a particular query, let's say the users randomly clicked on some ad. Now, it may or may not be relevant to the query, but since there was a click, you may basically consider it as a label, although it's an incorrect label. Okay. So different kinds of bias in the training data. So in fact, even so now how do you handle this bias is the question. So your training data, which we will call as which we'll call as Y here, this training data is noisy. Okay. So this training data Y basically is so if you have ads and you have keywords, it's basically that kind of a matrix. So it is zeros or ones, the binary matrix, and it's sort of noisy. Okay, it has missing labels and it has incorrect labels. However, if you basically think about a particular label, even if it was a missing label, some of its nearest neighbors were very likely to have that label. So quite likely it is not missing for nearest neighbors. Okay. So if this particular ad has a particular missing label, now if you look at semantically other related ads, maybe those ads basically don't have that label missing. So can you propagate that label from those similar ads to this point? Okay. So that is what you do. Infer the labels based on the labels of its neighbors, and there are standard ways of doing it called as graph-based semi-supervised learning. Okay. In fact, the way it is done is as follows. So essentially, from this matrix Y, which is the original label matrix, what you want to obtain is a smoothed out label matrix, basically also called as F. You know, uh, such that Y and F should not be very different from each other. So you do not want to basically completely ruin the label structure. I mean, there is missing there are missing labels and incorrect labels, but they're not completely wrong. Okay. So you basically want to ensure that your Frobenius norm between f and y is not very large. So essentially, you want to ensure that they are super close to each other, very close to each other. You also want to ensure that there's sparsity in the predicted matrix. So you don't want to, you don't want every label to be provided to every data point, right? So essentially, therefore, there should be sparsity. So therefore, the L0 norm must be less than equal to L, some bound. Okay. And then what you also want to do is to do label propagation. So here, if you notice, W, essentially W is the similarity between two training points. So remember nearest neighbors, you have to do label propagation from nearest neighbors. So W is the similarity matrix between two training points. And it is based on intersection of their label sets itself. So looking at label sets itself, you can sort of come up with label correlation in some ways. And that's basically is the matrix W. Now D, so D is basically a diagonal matrix representing the row or the column sum of W. So it's a diagonal matrix. It represents either the row sum or the column sums of W. So that's basically that. And what you want to do is to optimize this function so as to minimize this value and find the right F. Find the right F. Okay. So once you find the right F, basically you train your MLRF, random forest on this smoothed out data set, and that gives you much better results. Okay. Now, how do these tree-based MLRF method perform? So, well, it is observed that compared to the KEX method, remember I told you in the beginning, KEX plus KSP is better, and then MLRF is even better. In fact, MLRF plus semi-supervised learning, as we discussed on the previous slide, is even better. And MLRF, semi-supervised learning, and KSP are the best. Okay. Here are some results on automated and human evaluations. This is automated evaluation. This is human evaluation. Uh, and these are four different data sets on which they evaluated. Some of them are ads data sets, some of them are web-based query documented click data set and Wikipedia category data set and Wikipedia title to category data set and so on. Right. So what they observed, the observation is pretty much this trend that MLRF plus SSL plus KSP leads to the best results. Okay. These are essentially precision at 10 values, which are plotted in this table. Now, interestingly, since you're talking about ad matching problem or add to keyword recommendation problem, MLRF actually picked the common trick of recommending a competitor's bid phrase. So essentially, if you have to show your ad, you should actually bid on your competitor's bid phrase, right? I mean, so as to basically show your ad when people search for your competitor's brand. Okay. So in MLRF, Geico actually bid on Allstate's phrase, Allstate car insurance coupon code, and MetLife actually bid on Geico insurance. So in the sense that yes, MLRF naturally can actually recommend competitors' bid phrases as good bid phrases for showing your ad. Further, human evaluation basically showed that these recommendations were more specific, targeted, and relevant. Okay. Now, all is good. So MLRFs are a great method. However, training MLRFs is slow. So remember I told you that it takes a day on 1,000 nodes to be able to train MLRF on about 90 million training points with 10 million labels. Okay. So can you come up with a faster tree-based method just to solve this problem? So, and that is what is called as fast XML. So in this method, you can actually train on 1 million labels on a standard desktop machine in 8 hours using a single core. Of course, who has a single core machine these days? So if you have multiple cores, of course, you can scale and then do it in much lesser amount of time. Okay. And that is why no wonder why it is called fast XML. Okay. It learns a hierarchy over the feature space just like MLRFs, and it also learns an ensemble of trees just like MLRF. And again, just like MLRF, the predictions are made by returning the rank list of the most frequently occurring active labels in all leaf nodes in the ensemble containing the novel point. So essentially, when a new test point comes in, you pass them through all the trees in the ensemble, reach the right leaf, and then look at the leaf's label distributions, aggregate them, and predict the most frequent ones. Okay. The only thing that differs in FastXML compared to MLRF is the optimization loss, optimization function, right? Rather than optimizing for Gini index, basically FastXML basically optimizes for NDCG at L. L being the number of labels, right? So essentially, FastXML actually optimizes for NDCG at L. Okay. So let's see how does it do this. So essentially, yi is labels associated with the data point I, and basically, it is and it's a vector of size L because for every label it has a 0 or a 1. Okay. Now in that case, if I were to compute the NDCG between the actual label between the actual labels that are present, label ranking vector R, ideal label ranking vector R, and the Y which is predicted. Um, uh, the way you would compute DCG, so this is not NDCG. So remember, NDCG stands for normalized discounted cumulative gain. It's a very popular metric which is used for ranking, right? So NDCG basically is DCG divided by IDCG. Now, where DCG stands for discounted cumulative gain, and IDCG is ideal DCG, ideal discounted cumulative gain. So if you basically notice the way DCG is computed is essentially you have YRL divided by log of 1 plus L. So this is basically position discounted. So this is the position discount. And since this is adding up, it's called cumulative. And here, essentially, you have normalized. So normalized because this is not normalized. Well, you will do normalization when you actually divide it by the IDCG. Okay, so that's that. Now, so in this particular case, y can be only 0 or 1. So therefore, typical NDCG is 2 raised to relevance minus 1. But since R can just be 0 or 1, it's basically just YRL. So it's basically 0 or 1. That's it. Okay. So that's that. Now, of course, equivalently, you can define IDCG. So that's basically what is defined here. So that's IDCG. And then once you have the IDCG, you can actually, you have defined IDCG as a factor here. So which is actually defined there. And then you can do DCG divided by, so this is the same factor as this factor. So you can do DCG divided by IDCG, and that basically gives you the overall NDCG loss. Okay. Or the NDCG metric. I mean, if you do a negative sign around it, basically it becomes a loss. That's it. Okay. So what you want to do as part of FastXML optimization is basically you of course want to split a node. So you essentially have a tree node and you want to split it. I'll come back to this optimization later. But what you want to do is you have a tree node and you want to split in the feature space so as to get a left child and a right child. Okay, of course. Now, the way you want to do that, though, is that you want to optimize for NDCG that can be made possible thanks to these two kits. Okay, so NDCG of the rankings that can be obtained, recommendation rankings that can be obtained for this particular for all the training points in the left child and the right child, of course. Okay, so what you want to do is to essentially in the feature space learn a separator. So learn a separator just like an SVM, such that essentially whatever is on the left side of the separator goes to the left child, or whatever is on the right side of the separator goes to the right child. And the separator is learned in the space of the users or space of the inputs. Okay, you don't learn it in the label space. No, I mean, just like in MLRF, if you basically do separation in the feature space, automatically that leads to separation in the label space. Not disjoint separators, but in the label space. But well, it does happen that way. Okay, more or less. So what you want to do is to learn a nice separator, and we are going to represent the separator using W. So this is what you want to learn. So you want to learn those weights W, coefficients W, just like in an SVM, right? You want to first do, regularization to ensure that these things don't grow too large. So L1 regularization. But what you want to really do is to ensure that you minimize W and you also maximize NDCG, okay, across all the data, all the training data points. Okay. And just like in SVM, you of course have a hyperparameter so as to weigh the regularization versus the complexity of the classifier versus the training loss, right? So that's that. Now, this particular NDCG that you see here can be actually split into two parts depending on the left child and the right child. So this is the NDCG for the right child, is the NDCG for the left child in that senses. Uh, of course, you also want to ensure that the similarity of the features, similarity in the feature space between W and X is higher on either of the two sides, right? So essentially, if W transpose X is less than 0, I mean, in both these cases, this value should essentially be minimized. This value should be minimized, the overall log loss in that senses. Okay. So that is that. So in FastXML, the difference from MLRF is only one, and that difference is basically rather than optimizing Gini index, you're trying to optimize NDCG. While doing so, you want to ensure that the overall NDCG of your retrieval, basically the overall NDCG of your recommendation of items to users or bid phrases to your ads basically is higher. Okay. Of course, ideally, you would want to just do that based on the leaf nodes, because leaf nodes is where the prediction actually happens. But the idea is that you start doing it right from the root node, so that when you reach the leaf node, these NDCG optimizations are the best. I mean, clearly, you cannot really do a global optimization just because it becomes combinatorially explosive. So essentially, therefore, you do it in a greedy manner, just like any other decision tree building algorithm. Okay. Now, how does the prediction happen? The prediction happens just the same way as in MLRF. For a new test point, you essentially take FastXML's top rank K predictions by using this formula. And this formula is exactly the same as what was done in MLRF. You take the test point, you pass it through the tree, reach the leaf nodes. In the leaf node, you basically look at the distribution of the labels, and then you just aggregate over the distributions and take the labels which rank the highest. Okay. So how does FastXML perform? So FastXML, of course, performs faster. So it is way, way faster compared to MLRF. And here are results shown on 4 different data sets, NDCG at 5 results. And 5 different algorithms are compared here. One versus all is essentially the dumbest method here, essentially, learning a classifier per label in that senses, right? Now, what you observe here is that there's FastXML and FastXML-T. So FastXML-T is with tuned hyperparameters and FastXML is without tuning. So what you observe is that if you tune FastXML-T, it basically performs way better than MLRF, which performed in general better than other methods, okay, all across these datasets. So FastXML is faster. It leads to better results compared to MLRF. In 2014, this was the best method which is available for doing extreme classification. It leads to more balanced trees compared to MLRFs, and prediction costs are logarithmic in the number of labels. Okay. Now that's all again good, but there is yet another problem to solve, and this is the problem of missing labels. So every data point has missing labels in its ground truth labeling, every data point, right? So for example, if you look at a problem, another problem, let's look at the Wikipedia problem. So the input is a Wikipedia page, and the labels that are expected are the tags or the categories that you want to put up on the Wikipedia page. Okay. For example, for Divine Comedy, you would want to say it's a book, it's a popular book, and you would want to say that yes, 1321 books is basically a good label for it, or 14th century Christian text is a good label for it, and so on. Okay, so that's that. Now, as I mentioned, every data point has missing labels in its ground truth labeling. Especially tail labels go missing very, very frequently, just because it's sort of difficult to remember all the 1 lakh categories, or all the large set of categories. It's very difficult to remember the entire label space for any human and then provide the right labeling. Okay, so every data point has missing labels. And infrequently occurring tail labels have little training data and are harder to predict also. So not just that the labels are more prone to missing in the tail. By tail labels, I mean labels for which there are not enough data points. Okay. Also, the idea is that if you look at infrequently occurring tail labels, which are which have less number of data points, they have very little training data, and therefore it's very difficult to actually obtain very high accuracy. So that's called as the tail XC problem, the tail extreme classification problem. That extreme classification suffers from sparsity in the tail a lot. Right. Uh, Also, I mean, if you look at a typical classification, multi-level classification setups before extreme classification kind of setups, if you have, let's say, 20 genres of movies and you want to predict which of them apply, people have used this popular loss function called as Hamming loss, where people have penalized, wrong labels being predicted as much as labels being missed, correct labels being missed in prediction, right? However, in extreme classification, the idea is that the label set is very large, and for a particular data point, only a few number of labels apply. So therefore, rather than caring about all the labels, negative labels also, you only care about positive labels. Okay. So therefore, in XC, due to relevant label sparsity, it is more important to accurately predict relevant labels rather than irrelevant ones. You ignore those null or irrelevant or negative labels completely. Okay. So that's a little difference. Um, Now, let's see what happens when labels go missing uniformly at random, right? So essentially, let's say there were labels associated with users. So users like items, and essentially this is a rating matrix. Okay. So there are these labels, and this matrix basically there is nothing missing. Okay. So essentially, in this particular part of the slide, we left part of the slide assume that nothing is missing. So all labels are observed in the ground truth, and essentially what you see here is essentially predictions which are made by some algorithm. And let's say this algorithm is a very dumb algorithm. It's like a constant recommender. It sort of recommends apple to everyone and also banana to everyone, right? So that's that. Now, if I try to compute the precision in this case, I have to compute the precision at 2. Let's say precision at 2. So basically saying that, hey, two things that were prescribed by the recommender, are they correct or not? Okay. So I have to basically average it over all the users. So there are 4 users, so therefore 1 by 4. And then I have to also care about, what is the precision for each of those users. So for the first user, well, she basically likes the apple and banana. So therefore, 1 plus 1 divided by 2. So both of them are correct. Similarly, if you look at all of these 4 users, well, the predictions are all correct. Okay, so therefore the precision is 1. Okay. Now let's look at a setup where the observed ground truth essentially has 50% of those labels only. 50% are missing. What happens in those cases? Okay. So as you notice here, 50% of those labels are gone now. Hey, by the way, in the left side, when I basically had like empty things, they didn't really mean that they're missing labels. It just meant that that she does not really like grapes. That's all, right? So in this case, now the labels are actually missing. Okay. So she likes grapes, but it's just that, or rather, she likes banana. It's just that we don't have that label here. It's gone missing. Okay. Now, in this case, when the predictions are made by the system, the constant recommender system, unfortunately, 4 of its predictions out of 8 are wrong, which basically leads to precision as half. So how do you solve this missing label problem? So, this paper basically came up with this interesting idea of unbiasing, of coming up with an unbiased estimate of the predictions of the precision, unbiased estimate of the precision, right? So essentially, and the way that they do is very, very simple. So the idea is super simple, the way it is implemented. Of course, the theory is complex, and therefore you can actually look at the theory. If you are mathematically oriented, go ahead, look at the paper and read the theory, right? But then the implementation is super simple. So all they suggest to do is to basically take every label, and for every label that is correctly identified, assign a weight of 2 for each correct prediction. Okay, so correct prediction will assign a weight of 2. So you would say that for this particular user, well, you get 2 points for predicting this correctly. Okay, and now of course you get 0 points for predicting something incorrectly. So 2 plus 0 divided by 2. Now in that case, your overall precision comes out to be 1 again. Okay. as is, the algorithm was correct. It was basically predicting correctly. Precision was supposed to be 1, but due to missing label problem, precision turned out to be less than 1. Okay. But this unbiased, this change that you made by actually giving 2 as the weight to every correct prediction basically helped in coming up with this propensity scored precision or an unbiased estimate of precision. Okay, so I mean, so why basically divide by 2? Now we divided by 2, and the dividing, or rather, considering 2 points for every correct prediction. We did this considering 2 points for every correct prediction um, just because, I mean, this particular value is actually called as propensity, just because we sort of thought that each label is missed at random 50% of the times. Okay, so that is why essentially we divided by we basically weighted by 2 in that sense. Okay, so formally this particular notion is called as propensity. So what is propensity? Propensity is the probability of a label going missing. So propensity is the probability that actually the label should be there, should be 1, but the label turns out to be you know empty. So, propensity is the probability that the label is present given it should be present, and 1 minus propensity basically is what is the probability that it is missing, right? So that's that. Now, well, you assign a weight of 1 over PIL, 1 over propensity for each correct prediction, and that is what you do in a scenario where labels have where the propensity values are different per label. So it's sort of bad to assume that each label goes missing with the same probability, and therefore, based on the probability with which they go missing, you essentially have different propensity values. Okay. So you assign a weight of 1 over PIL for each correct prediction, where what is PIL? Well, PIL is the probability of the label being present given that that was the true label. Okay. So for example, in this particular case, if you basically look at look at this particular case, well, if you consider Apple, so if you consider Apple, Apple was supposed to be present in all 4 cases, but hey, it has gone missing and it appears just once now. So therefore, you essentially multiply these propensity value, these precision values 4 times. Similarly, if you basically consider another label like grapes, it basically was supposed to appear for 2 times, right? But it sort of appears only once. And therefore, if you had something correct for grapes, you would have multiplied by 2 times. And then same goes for banana and so on, where you have different propensity values for different kinds of labels. Okay. So that's that. So the propensity is essentially the probability of the label being actually present, given of being present in the training data, given that it truly was present, right? Now, the interesting part is that the way propensity values are computed is as follows. They're actually computed using this formula. Um, and the way this particular curve is fitted so as to understand the values of A, B, and C. A, B, and C are constants, by the way, right? And NL essentially is the number of data points associated with the label L. Remember, propensity is a function of the label, and it is computed using this formula and or rather this form, right? And where it depends on NL, how many data points are annotated with that label. So the propensity value differs based on whether it is a rich label in this or a head label or a tail label. So if many data points are annotated, NL value is larger, else the NL value is smaller. Okay. Now, what these guys did was to sort of estimate the values of A, B, and C by fitting to the true values which are observed in the data sets, in the Wikipedia data set and and on Amazon data set. Okay. Now, the idea is that you might be thinking that, hey, if the labels have gone missing, then how would you really know what are the true labels anyway? Okay. So interestingly, it turns out that if you look at Wikipedia pages, they are tagged with some labels. Okay. So for example, the page for Mumbai could be labeled as an Indian city. So Indian city is a label for it. Okay. So interestingly, what they did to get the true label set is use this simple heuristic. If a label is relevant to a Wikipedia article, then so are all its ancestor labels. So for example, if cities is a broader label, and if Mumbai is only tagged with Indian city, now Indian city is surely a city, and therefore you can basically say if cities was not tagged for Mumbai Wikipedia article, then that's a missing label. and that should basically be considered as a true label as well. Okay. So based on that, that's how they basically created this curve, these plots for Wikipedia, where on the x-axis you have log of NL, and the y-axis you have the PL value, the propensity value, right? And then after you plot that, you basically fit this curve and then get the values of A, B, and C. Well, A and B, and then C is actually defined once A and B are already set. Okay. Similarly, they could do it for Amazon. So Amazon, of course, you have categories and product recommendation on Amazon. So so in the Amazon data set for every particular product, the label set is all of the products that can be recommended for this particular product. Okay, so it's like an item to item recommendation problem. Now, if you look at just the recommendations, they are incomplete in nature because they basically just show a few of those, so they're incomplete in nature. But if you actually also look at other things like also viewed and also bought, those can help you complete the set of recommendations and therefore get a two label set. That is what they did, and they basically got those. Plotted this curve and therefore obtained the right A and B so as to fit for the Amazon dataset. Okay. Now, based on all of this missing label problem and the propensity scored losses that were defined so far, the fast XML algorithm was modified to come up with a propensity-based fast XML algorithm. Okay, the algorithm does not differ much. It's just the same algorithm. Rather than optimizing for NDCG, you start optimizing for propensity scored NDCG. Okay. It still has ensemble of trees. It basically still does all of that partitioning, creating that separator based on NDCG rather than NDCG. Now it does on PS NDCG, which is propensity scored NDCG. Okay. The loss gives so if you basically look at essentially the formula, this thing remains the same. The optimization function remains the same. There is you want to make sure that the separator does not really have very high weights. You also want to optimize for the log loss, and then you want to ensure that you maximize your NDCG values, or maximize your NDCG values or minimize the NDCG loss, right? For both for the left node and for the right for the left child and for the right child, right? So that's that. Now, if you look at the propensity weights that are available, that basically become a part of this entire scoring, remember the propensity weights basically depend on NL. So essentially, rich labels are going to get different weights, and tail labels are going to get different weights. So that's that. Now, if you look at Wikipedia, on the x-axis you have NL. So the tail labels are log of NL. The tail labels are on the left side. The rich labels or head labels are on the right side. And as you notice, the weights. So it basically gives very high weights to the tail labels and lower weights to the head labels. That's basically the way you can read it. That's the red curve. Okay. So the propensity-based loss essentially gives higher weight to rare items, thereby learning much better for rare items. It sort of also solves the tail XE problem to a certain extent. Okay. So low tail label accurate. However, even though all this is done, sometimes what turns out is that your tail label accuracy is still low. Because when you do tree-based partitioning, these partitioning errors in the internal nodes sort of disproportionately reduces the support for tail labels in the leaf. So therefore, in the leaf node, when you have to make those decisions, those decisions are made on actually very small number of data points. Okay. So therefore, what they do is to re-rank the outputs that you obtain from this propensity score-based fast XML algorithm. You take those predictions, you re-rank those predictions using classifiers which are specifically trained for tail labels. Okay, and that leads to this algorithm called as pfast re-XML. So re-ranked XML, also called as faster XML. Okay. Now, how does faster XML perform? So they basically evaluate the performance on several data sets. I'm showing here performance on URLEX dataset. URLEX dataset is a rather small data set, not too many labels, not too many data points, so easy to experiment with. Okay. They assume that the URLEX dataset has no missing label. So they assume that URLEX dataset has complete ground truth and there's no missing labels. And then they simulated the missing label problem by actually randomly removing some labels, and that gives you missing label dataset. Okay. Now, then they did various experiments. So for example, in this particular experiment, you see on the y-axis is NDCG at 3, and on the x-axis is percentage of missing labels per point. So now if you basically have And then there are three methods here, right? So NDCG at 3, NDCG at 3 without missing labels, and propensity scored NDCG at 3. Okay. So if you look at NDCG without missing labels, that's basically, of course, flat, because the NDCG value does not, the red curve is flat because NDCG value then does not really depend on the percent of missing labels at all. Okay. Now, if you look at NDCG with missing labels, you basically observe that your NDCG value keeps dropping, right? Because labels are missing. So you do predict the right things, but you don't get brownie points for it because the real ground truth has missing labels. Right? But if you do propensity scored NDCG at 3, you essentially have the green curve overlapping with the red curve, saying that, hey, propensity scoring sort of makes up for the loss in terms of missing labels. Okay, so propensity scored NDCG at K is therefore unbiased in that sense. Now, the second comparison here is in terms of percentage of missing labels per point and NDCG at 3, and you compare fast XML versus pfast XML, which is the propensity scored fast XML, and you observe propensity scored fast XML typically gives you good results across different values of percentage of missing labels per point. Okay. The third experiment they do is, of course, you basically came up with these A and B values for these two data sets, A, B, and C. So Wikipedia as well as Amazon. What if you have a new data set and you don't really know how to compute A and B for it? Okay, because you don't have any ground truth as such, right? So in those cases, what it did was to basically compare three algorithms here. On the x-axis, you have varying A value. So you vary the value of A. On the y-axis, you have NDCG at 3, right? And the three algorithms are fastXML, pfastXML2, and pfastXML. Okay, so essentially fastXML is flat, of course, because with A it does not really, it does not really do any propensity scoring. So therefore, there is no reason why it should vary at all with the value of A. Okay. Similarly, pfastXML2 is also flat. Why? Because, well, it does not really depend on A. You have fixed A, and that's basically the one that you use. The green curve is basically what happens when you vary when you vary the value of A. Okay. So what do you observe? You basically observe that the green curve always remains on top of the red curve. So what this means is that irrespective of whether you decide the values of propensity coefficients properly or not, you still will get better results compared to using fastXML, which basically does not use propensities at all. Okay, so training using incorrect propensities might actually be better than training without propensities at all. Okay. And then, on this URLX data set, they actually compared with the several other extreme classification kind of methods, and they found that pfastXML gives them better results on all of these propensity scored matrix, right? Propensity scored NDCG at 1, NDCG at 3, NDCG at 5 matrix. Okay. So that's it. That's it for this video. In this video, in summary, I talked about tree-based methods for extreme classification. Specifically, we talked about three different methods: multilabel, random forest, fastXML, and pfast re-ranked XML. The way that these three methods basically differ is in terms of the loss function that they use. MLRF uses Gini index, fastXML NDCG, and pfast re-XML, propensity scored NDCG. That's it. So hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.